I'm Shahar Papini from StarkWare. I work on the compilers team and worked on Cairo. And I'm here to talk to you today about how not to build a compiler. The story of Bob. That's a slide. The story is based on true events, but all the names, the characters, the incidents, everything is fictitious, so don't worry about shaming anyone. This is Bob. Bob wants to build a compiler for the Bob language. This is an example for the Bob language. It has a Bob func called Robert. It gets a Bob object, etc. Bob grabs his favorite Dragon book, which is a classic compiler's book. In it says that the compiler is a program composed of 3 parts. First part is a parser. This one reads source code and outputs a syntax tree. Another one is a type checker. It goes over the syntax, it checks all the types, adds type information onto the syntax. And third part is an emitter. It's a part that takes the tree and its semantic information and emits machine code in the end. Bob built it and he was happy. It worked. Nice compiler for the Bob language. Bob starts to write some code. Bob gets an error, missing a semicolon on line 2. He has semicolons in his language. All right, he fixes the error. He adds this semicolon. Then he gets another error, missing semicolon on line 3. Bob is a bit frustrated. I mean, he doesn't want to fix every error one at a time, then gets the next one. He wants all of the errors at the same time. Okay, so Bob here's a good solution for this is to make an infallible parser. What does it mean? Instead of making maybe a classic parser that whenever he has some syntax error fails and just bails out, he builds a parser that never fails. Instead of failing, the parser tries to recover from its own errors. It always returns a syntax tree. The syntax tree might be partial, might be missing some nodes at the middle, but also always brings some syntax tree. And along this partial syntax tree, he brings some accumulated syntax errors as it goes. All right. So here's an example. For this code we saw at the beginning, the syntax tree might look like this. It might have a function. Inside this function, he has statements like call and call. Inside this call node, he has the name of the function, the parameters list, and a node that was supposed to be semicolon is now just missing semicolon. So it's a partial syntax tree. It has a missing node. All right, he does it. Bob now gets all the syntax error right away. And Bob was happy. Has a nice compiler. Bob starts to write some new code. He types this code, starts to write Bobby.b, and Bob forgets the name of his function. Oh no, Bob has no autocomplete. Bob is sad. Bob wants autocomplete. All right, so Bob decides to add some IDE integration. IDE integration is the thing that highlights your code in your IDE, does the autocomplete, has good definition, all these nice features when you're developing in your code. So you get all these features from the IDE integration. And modern IDEs actually use a language server protocol, which is kind of a unified protocol for compilers to give access to IDEs to all kinds of features. So Bob decides to write a language server for the Bob language that will also support autocomplete. All right, Bob writes a language server. Like a sane person, he decides to reuse his compiler code. Okay, one of the things that have been done a lot in the past is rewriting all the parsing, all kinds of semantic information for the language server. But it doesn't make any sense, so he decides to share his code. And he refactors his compiler. His compiler is now no longer a single program. Instead, it's an API library that exposes all kinds of API regarding syntax and type info for his program. All right, he did it, and it works. He can get all kinds of completions, nice completions for his Bobby object, and he was happy. Bob writes a lot of code in the Bob language. Every time he autocompletes, all project is type checked. Every time he presses this little tab for autocomplete, he needs to wait a few minutes because everything needs to get type checked. That is how it was written at the beginning. So Bob is sad. It's too much time. All right, Bob decides to use a query system. What does it mean? Usually, when you type in the IDE and start developing, code changes are very local. So most of the type information and syntax information, most of this is still relevant. It still doesn't really change. Just a very small part of your program is changing. So we want a way to only recompute the things we need and to cache the things that don't change. This is where query system comes in. Basically, Bob takes his compiler and breaks it into a lot of small query functions that call each other. We cache these results, and when we have some small change or any change, the query system is responsible for updating exactly what we need. And let's see some example. Let's say this is how we break the compiler code. Example function. Let's say we have this get function semantic info. It gets a function and returns all the type info inside this function, what it returns, what it gets. This one depends on the get function syntax, which for every function returns the syntax tree. And this function, get function syntax, actually depends on get file syntax, which is the function that gets the syntax tree of the entire file. So this function calls, this query calls this query, this calls this query. All right. What happens when Bob adds some code right after this function? Well, the get file syntax needs to be recomputed. Why? Because it depends on the file content, and the file content was changed. So get file syntax is invalidated and needs to be recomputed. So it gets recomputed. Next one is get function syntax. The file syntax was changed, so the input to this function is changed, so it needs to get recomputed. But the return value of get function syntax actually returns the same as the previous value. So basically, the output of get function syntax is essentially unchanged. Even though it was recomputed, the value it gave is unchanged. So this is where the query system comes in and knows, this function doesn't need to get recomputed because this input is exactly the same input. So this is how a query system works, and this keeps all the computation to only what we need, and for other parts of the code that are not changed and don't need to be recomputed, to use the cached values. All right, Bob's language server is a lot faster now. There's still some room for improvement. It's still not as smooth as it can be. So he looks again. Bob's code is somewhat inefficient. When he needs to refer to language items inside his code, he uses pointers. For example, when he has some Bob call statement, which calls a function, the representation inside his code has some pointer to the callee function. His expressions have a pointer to their type struct. The keys for the queries you just saw, these small functions that call each other, the keys are also pointer. For example, the get function syntax, it got a pointer. And what does this mean? This means that when we need to compare such pointers, for example, if I want to understand if two types are equal, I need to do something recursive to dive into the values and decide if this this, are both structs, is the first field of the same value, etc. Or if the same function, also I need to dive in to understand if it's the same thing. Also, when I hash, I need to hash them if there are, for example, query keys. Like I said, queries we are caching. We're caching queries by the inputs. So if the input is some pointer to a function, we need to compute this hash for this entire function, which also is recursive, looks at all the fields, and might be expensive. Okay, so instead of using pointers to type, to function, to whatever, Bob decides to intern his values. What does interning mean? It means he keeps a table of all the type instances he has seen. When he needs to refer to some type, he first looks it up in the table, searches if it already exists. If it does exist, then he uses the index of the existing type to be used as type ID. If it doesn't exist, he allocates a new type on this big table and uses this as a type ID. So basically, now instead of using pointer to types, he uses this type ID. With the property, also the type ID is very small, just an index, and it provides the identity of this type. For example, if we have two different type IDs, they're definitely not the same type because we used interning. So this is like the identities he right now uses for everything, not just types. He has function ID, he has struct ID, anything. And now comparisons and hashes are very fast. So Bob's language server is really fast now, and he is happy. Bob now tries to build an analyzer for the Bob language. For some reason, he wants to have exactly 303 Bob variables in his code. I don't know why. He builds an analyzer that traverses the syntax tree. His analyzer needs to handle all the kinds of syntax nodes he can see. Bob ifs, Bob fors, Bob lets, Bob jumps, everything. And that's a lot of code, a lot of maintain, a lot of complexity. Bob doesn't like it. Bob is sad. Bob adds a compiler phase to make it simpler. What this compiler phase does is reducing the big Bob language into the simple Bob language. In this, the transformation is taking things like Bob ifs and converting them to Bob jumps. Also, Bob fors are converted to Bob jumps. And instead of a lot of syntax nodes that are relevant for the high-level language, simple Bob is using very simple construct, as little construct as possible to still stay expressive, but we want it to be as simple as possible. And after this transformation to simple Bob, only then simple Bob gets translated to the Bob machine code with Bob instructions. So instead of going straight from the Bob language to Bob machine code, it goes to the simple Bob language in the middle. The benefit he gets from it is now that his analyzer only needs to go through the simple Bob language. And now, instead of handling Bob ifs and Bob fors and Bob lets, the analyzer only needs to handle Bob lets. So it's a lot less code, and it's easier to write. And he's happy. He's very happy. What about errors? Bob wrote a code with a mistake. He tries to use the Alice method in Bob. I mean, who is Alice? I know who is Alice. Alice is not found. Quickly, before anyone sees, he tries to get auto-completions, but fails. The mistake he actually made the type checking phase completely fail on this function. Again, the original design was as a single program, and type checking was allowed to bail if you had any error. But that also means that even we have some mistakes, some semantic mistakes in our code, then we get no semantic information for this function whatsoever. So Bob decides to refactor his type checker. Now, when he has semantic errors, instead of just bailing, they try to corrupt as little information as possible they don't fail the computation. The computation still succeeds. You still get some partial semantic information with as much semantic information as possible. Type errors are propagated. This is kind of similar to what we did for the syntax. Okay, now Bob does it. It works. Bob quickly fixes the error before anyone notices, and calls the Bob method on its object, like it should be. All right, Bob was happy. No, but who knows what kind of adventures lie ahead? What kind of bugs he will meet, inefficiencies? Only time will tell. Okay, so this nice story was inspired somewhat, but by our efforts to write two compilers. We wrote the Cairo 0, which wasn't planned at the beginning as a high-level language. Instead, it was a kind of assembly that we added and added and added to like higher and higher features. But we didn't have this planning from day one. A lot of issues we encountered kind of resemble Bob's. Cairo 1 was planned a lot better from scratch with high-level compilation in mind, with model compilation design, with language server. So it encompasses a lot of things we learned from our journey. All right. Any questions? Yes.
Shall I wait for a microphone or shall I?
I don't know. Microphone is on the way. Yeah.
Thank you.
Hey.
So some parts of this journey resemble pitfalls and problems that the Rust language also had. Is that a common experience with many languages, or is it something that you shared specifically with Rust because of the common origins and orientation?
It's a good question. Like I said, a lot of languages don't really use modern compilation ideas in mind, and you can see it also in the fact that they have separate language servers that are using different implementations. Now, a lot of modern things like C# compiler was really one of the groundbreaking, I think, that used a lot of these ideas, and this is like, I think, one of the origins of these ideas. And the Kotlin compiler also uses similar things. Rust Analyzer uses similar things. So not everything, but some things that are not necessarily Rust also has this. Okay, thank you very much.